What if a tiny spacecraft is currently racing through space to catch ancient asteroids, relics from the dawn of our solar system, with the goal of bringing back pieces of the cosmos itself? This is no sci-fi fantasy, but reality. This mission is China's Tianwen-2, a bold and groundbreaking asteroid exploration mission that could reshape humanity's understanding of the universe and our origins. China's space ambitions have rapidly expanded in recent years, with Tianwen-1 achieving a successful Mars landing that amazed the world. But the nation's next giant leap is even more daring. Tianwen-2, an asteroid sample return mission aimed at investigating some of the oldest, most mysterious objects orbiting our sun. Asteroids are more than just space rocks. They are frozen time capsules that hold clues about the birth of our solar system 4.6 billion years ago. Studying them up close can reveal secrets about planet formation, the delivery of water and organic compounds to Earth, and the preconditions necessary for life. Tianwen-2 takes the mission a step further than many before it by targeting not just one, but two asteroids. A near-Earth asteroid named 469219, Kamo-o-Alewa, and a much larger main-belt asteroid called 511 Davida. Asteroids are remnants from the early solar system, leftovers from the cloud of dust and gas that formed the sun and planets. Unlike planets, these bodies have remained mostly unchanged, making them natural archives of ancient material. Among the most exciting reasons to study asteroids is the possibility that they brought water and organic molecules to early Earth, potentially jump-starting life. Yet many questions remain. What are asteroids made of at their core? How did their compositions vary across the solar system? Could they have delivered the raw ingredients needed for life? How do different asteroids compare in terms of mineralogy and chemistry? By bringing samples from these celestial bodies back to Earth, scientists can use sophisticated labs to analyze their composition in unprecedented detail, far beyond what any remote spacecraft instrument could do. Tianwen-2's primary target is the near-Earth asteroid 469219 Kamo-o-Alewa, a tiny, roughly 40-50 meter wide rock orbiting the Sun in a unique pattern alongside Earth. It's classified as a quasi-satellite, meaning it appears to orbit Earth but is actually orbiting the Sun in tandem with us. Kamo-o-Alewa is a prime candidate for sample return because its close orbit makes it relatively accessible, and its composition is still a mystery. Capturing samples from this asteroid could reveal what small near-Earth objects are made of and how they've evolved over billions of years. But the mission doesn't stop there. After completing its operations at Kamo-o-Alewa, Tianwen-2 will continue its journey deeper into the asteroid belt to study 511 Davida, a much larger and ancient asteroid around 270 kilometers across. Davida belongs to the main asteroid belt between Mars and Jupiter, a region filled with millions of space rocks that hold clues about early solar system processes. Studying Davida remotely allows scientists to compare near-Earth and main-belt asteroids, expanding our understanding of the diversity and evolution of these primitive bodies. The mission has several core scientific goals. First, sample collection and return. Land on Kamo-o-Alewa, gather surface samples of soil and rock, and return them safely to Earth for lab analysis. Second, remote sensing of 511 Davida. Use advanced imaging and spectrometry to map Davida's surface composition and physical properties. Third, characterize asteroid geology and mineralogy to understand surface features, composition, and space weathering effects. Fourth, study asteroid dynamics and orbit. Measure gravitational field, rotation, and interaction with solar radiation to better predict asteroid trajectories. Lastly, contribute to planetary defense. By understanding asteroid composition and behavior, the mission can improve models that help predict potential Earth impactors. Tianwen-2 is a highly complex spacecraft equipped with cutting-edge scientific instruments and autonomous navigation technologies. Key systems include multispectral imagers and spectrometers to capture detailed images and analyze the asteroid's surface composition in visible, infrared, and ultraviolet wavelengths. It also carries a lander and sampling mechanism designed to briefly touch down on Kamo-o-Alewa's low-gravity surface, scoop or drill samples, and launch the sample capsule back to the orbiter. An autonomous navigation system is essential due to the long communication delay between Earth and the spacecraft, allowing it to perform delicate maneuvers independently. The sample return capsule is a highly secure, heat-shielded container that will protect the precious asteroid samples during their fiery re-entry into Earth's atmosphere. Solar panels provide energy, while ion thrusters or chemical engines enable trajectory adjustments across millions of kilometers. Successfully landing on such a small body is incredibly challenging. The spacecraft must precisely match the asteroid's orbit and rotation, avoid surface hazards, and adapt to extremely weak gravity that could cause it to bounce off or lose contact. Tianwen-2 launched on launch date from Earth's surface, beginning a complex interplanetary cruise phase. The spacecraft follows a carefully calculated trajectory to intercept Kamo-Walewa, spending months or years studying and preparing for the sample collection operation. After successfully gathering the samples, Tianwen-2 will depart Kamo-Walewa and continue to Davida for remote sensing. Finally, the spacecraft will begin the return trip, releasing the sample capsule to re-enter Earth's atmosphere and land in a designated recovery zone. This entire process may span several years, with mission control monitoring every step and scientific teams eagerly awaiting the data and materials that could transform planetary science. Tianwen-2 joins a distinguished club of asteroid sample return missions, following in the footsteps of NASA's OSIRIS-REx mission to asteroid Bennu and Japan's Hayabusa and Hayabusa 2 missions to asteroids Itokawa and Ryugu. OSIRIS-REx launched in 2016 and recently returned samples to Earth, providing unprecedented insights. Japan's Hayabusa missions also succeeded in returning asteroid material, proving the technical feasibility of these missions. China's entry with Tianwen-2 marks a milestone that demonstrates its rapidly growing capabilities in deep space exploration, robotics, and planetary science. It also signifies a new era of global space competition and collaboration, where more nations contribute to expanding humanity's cosmic knowledge. Studying asteroids isn't just a scientific curiosity, it has profound implications for our future. Understanding asteroid compositions can inform future resource extraction, space mining, improve planetary defense strategies by predicting asteroid impact risks, answer fundamental questions about how water and life's building blocks arrived on Earth, and inspire new generations of scientists and engineers to push the boundaries of exploration. Tianwen-2 embodies human curiosity and technical prowess, a testament to how far we've come and a promise of discoveries yet to unfold. In the next part of this video, we'll dive deeper into Tianwen-2's scientific instruments, the challenges faced during the mission, the sample collection process itself, and what we can expect when those asteroid samples finally reach Earth. Stay tuned to witness how this historic mission unfolds, bringing us closer than ever before to the secrets locked inside the ancient rocks orbiting our sun. Now let's dive deeper into the heart of Tianwen-2's mission, its scientific instruments, and the remarkable engineering that makes this asteroid rendezvous possible. The spacecraft is equipped with a suite of advanced sensors designed to unlock the mysteries of both Kamo-Walewa and Davida. These include high-resolution cameras capable of capturing detailed surface imagery, spectrometers to analyze mineral and elemental composition, and laser altimeters to map the terrain with extreme precision. Together, these instruments allow scientists to build a comprehensive picture of the asteroid's geology, surface features, and history. One of the most critical components of Tianwen-2 is its autonomous sampling system. Unlike larger bodies such as the Moon or Mars, these asteroids have microgravity environments, which makes landing and collecting samples incredibly difficult. The spacecraft's lander is engineered to gently touch down on the asteroid's surface, using thrusters and robotic arms to secure itself and gather soil and rock particles. The sample collection mechanism can either scoop or drill beneath the surface to retrieve pristine material untouched by solar radiation or space weathering. Collecting samples in such conditions demands flawless timing and control, as any miscalculation could cause the spacecraft to rebound off the surface or fail to gather enough material. After the collection, the samples are sealed in a secure return capsule designed to withstand the harsh environment of space travel and atmospheric re-entry. But the challenges do not stop at sample collection. The spacecraft must navigate complex orbital dynamics to depart from Kamo-Walewa, adjust course to flyby or orbit Davida, and finally make the journey back to Earth. Each phase requires precise trajectory adjustments, powered by ion thrusters that provide efficient propulsion over long durations. Throughout the mission, Tianwen-2 continuously transmits data back to Earth, allowing scientists to monitor progress, make informed decisions, and prepare for the final sample return phase. Once the spacecraft reaches Earth's vicinity, it will release the sample capsule, which will enter Earth's atmosphere at high speed, protected by a heat shield. After a carefully planned descent, the capsule will parachute to a designated recovery area where scientists will retrieve the precious asteroid material. Once back on Earth, these samples will be studied in state-of-the-art laboratories using techniques far more sensitive and detailed than what any spacecraft instruments can provide. Scientists will analyze isotopic ratios, mineral compositions, organic compounds, and microstructures, all of which will help answer fundamental questions about the origin and evolution of the solar system. The implications of Tianwen-2's findings are enormous. For instance, understanding the composition and structure of Kamo-O'Alewa could provide clues about the early solar system's building blocks and the processes that led to planet formation. Studying Davida's surface and composition could reveal how larger main belt asteroids have changed over billions of years, and their role in delivering water and organics to Earth. Moreover, the mission's data will enhance asteroid impact risk assessments, improving our ability to predict and potentially deflect hazardous objects in the future. It will also inform plans for future asteroid mining ventures, which could harvest valuable metals and materials for use in space exploration. China's Tianwen-2 mission represents a new frontier in planetary science, showcasing remarkable international progress in space exploration technologies. By targeting multiple asteroids with a single mission, it pushes the boundaries of what is technologically possible and sets the stage for even more ambitious interplanetary endeavors. The mission is a testament to human curiosity, perseverance, and innovation. It highlights how international collaboration and competition drive the rapid advancement of space science, bringing us closer to unraveling the mysteries of our cosmic neighborhood. As Tianwen-2 continues its journey through space, the world watches with anticipation, eager for the moment when ancient asteroid samples return to Earth, carrying secrets that have traveled billions of years through the void. Stay tuned for more updates on this extraordinary mission as it unfolds chapter by chapter, revealing the profound stories hidden in the stars and rocks that orbit our sun.